So good morning, everyone. So welcome to my second session. So today I'll talk about artificial intelligence and mostly on the fundamentals of artificial intelligence. So uh, like in the background that you just heard, like the world is buzzing with the term artificial intelligence right now. It's everywhere. Everyone is using ChatGPT, BERT, or some other kind of very large uh, neural networks, basically neural networks, also called large language models, LLMs. Um, like every big company is developing their own LLM. Google has its own BERT, Facebook has its own called Llama, and OpenAI has its own GPT-4 or ChatGPT that started all this buzz with large language models. But today we are not talking about all those fancy things and all those complicated things. Today I'm just talking about the very basics of artificial intelligence, how this artificial intelligence thing is modeled, and the very basic unit used in artificial intelligence. I'll just talk about that. So the contents today will be just the introduction of the term, and introduction of intelligence. What is intelligence? What is cognition? Um, I'll talk about mathematical functions, the fundamentals, and then neurons, next fundamentals. And hopefully we'll build a single neuron for doing something useful, just one neuron. And finally, there will be a QA session. Uh, so at first diagram you see everywhere. So the artificial intelligence is a very big term. And the term that you are hearing everywhere. And another term you hear that is subset of artificial intelligence is machine learning. And another important or most powerful machine learning technique right now is deep learning. So we will focus on the basics of artificial intelligence, and finally the very basics of deep learning. So besides this machine learning, deep learning, there is some other artificial intelligence technique called symbolic AI that focuses on making logics. This machine learning, deep learning focuses on working with data and trying to find patterns in data. And symbolic AI is something else. It's like having a very complicated and huge if-else statement. But symbolic logic is also there. Okay, so first, I like to start everything with a history. So where did this word artificial intelligence, AI, came from? So this was first coined in 1955, so in a proposal. So the proposal was to start a new conference in a Dartmouth University here. So that objective of that conference was to design a machine that would be capable of thinking and reasoning like a human. So this John McCarthy first wrote that proposal and to gather scientists to design a machine capable of thinking and reasoning like a human. And there he introduced the word, the term artificial intelligence. And he believed that we will have some artificial intelligence in some 5 to 5,000 years. So very optimistic person. And this person is also creator of a language called Lisp, if someone is familiar. And Lisp was initially used for creating lots of engines to run artificial intelligence. Later, it was replaced by other modern languages, but Lisp was initially created for working with AI. So that is the origin of AI. But what does AI actually mean? And do we all understand the meaning of AI? So the AI simply means it's a simulation of human intelligence by machines. So primarily right now, the machines we are focusing on is computers or computing machines. So maybe like 200-300 years ago, so it might be some mechanical machines focusing on AI, but right now we have digital computing machines. And so AI is just the simulation of human intelligence. We want to mimic that intelligence, but what actually is intelligence? So there is this definition I copied. Um, so intelligence is nothing but a mental quality, and it consists of ability to learn from experience, adapt to new situation, understand and handle abstract concept, and use the existing knowledge to manipulate one's environment. So this is intelligence. Um, but so I particularly do not like the term intelligence that in the work that we are doing. I prefer the term cognition. So it should be artificial cognition for all the work we are doing. But intelligence is the goal, so it's acceptable to use artificial intelligence. So intelligence is a quality, and all the process is called cognition. So cognition is all the mental action and process of acquiring knowledge and understanding through thought, experiences, and senses. So that is cognition. And when we are building AI, so we are building a non-human cognition system. So the inspiration for everything, this cognition, artificial intelligence is the brain, of course, because we are intelligent and we are trying to create a next brain. So, but the problem is brain is one of the most complicated thing, and it's one of the least understood thing. So we know how the cells perform, how the muscle perform, and how signals are transmitted. But even to this day, we don't know how everything works together to make us, to give us that ability to learn, to understand abstract things, to connect things. So that is still a mystery. And there is this famous quote like that says, if brain was simple enough to be understood, we would be too simple to understand it. So because the brain is complicated, so we are having very hard time understanding that. So brain is the cognition hardware in human. So AI is building something that mimics the brain, very complex brain. And this the first how the cognition work, it was first proposed very early in around 400 BC by none other than Plato. So he proposed that human learn by association. So they associate one thing with other, and that is how they learn. Uh, so it's the same in all the organisms, and every organism, like even dogs, they connect one event with another. Like if you ring a bell every time before you give something to eat to a dog, then he will expect food when you ring a bell again. So this is called association, and this is how we learn and how we build intelligence. So this is one of the fundamentals. And what we are doing is we are associating two events and that occur together and storing that knowledge in our brain. So that is association. So, so one example is we associate everything. Like when there is heavy rain, we associate that with flood. Um, because we have seen or we have heard about this association. Now, how do we represent association as a scientist or as an engineer? Like association is you have one stimulus input and the outcome output. But how do you represent that? You represent it using mathematics. And specifically, you represent using something called function. So I think everyone has heard about function, use the function, solve the function questions in their school, high school, undergrad, graduate degrees. So functions are something that represent association. It takes input and you get the output. Here, we have a function fx, so that takes x as input and gives y as the output. So that is one way of showing function fx. Another popular way that I did, or I think most of us did during, I think, grade 9 or 10, we drew something called domain range and made arrows from one to another. So those are also function. So this all AI is also doing just modeling these function. So we have set of inputs, we have domain, and we produce some other outputs range, like we have stimulus, those are all domains, and we produce outcome, those are all range. So this is the next fundamental of AI, or fundamental of any intelligent system design. So you first have to model a system, and that model is a function. We know Plato postulated that we learn by association, and later we have mathematical tool to model association functions. But how does the brain actually work, and what do we know about the brain? So in early 1800, it was known that brain is formed by a very large number of interconnected neurons. So why early 1800s? Because the microscopes were strong enough in these 1800s, so that we could slice the brain, look into the brain, and see all the interconnected cells or neurons. So that is how we knew the brain had lots of interconnection. So, but the most interesting thing and most puzzling thing was all the interconnected neurons were a single unit, like they were not different. So everything was same, but they performed different tasks. Like we could see, we could remember, we could process speech, we could hear, and everything, all by using those neurons. So imagine in current computer, we have like very different units for different things. Like we have adders, multipliers, we have memories, separate input output controllers, everything. But here everything in brain, everything is just neurons, and all those neurons, strangely, they were one unit, a single type of unit, but different functions were defined by the connection between them. So this model was proposed, I think, around 1870 or sometime by someone known as John Minsky. No, sorry, I didn't put that in slide. Alex Bain, I think, Alex Bain, yeah. So in his book, Mind and Body, he proposed like everything is from the connections, and strength of connection chains, and the functions of the brain or group of neurons change. So this is the basis of AI that we are dealing with right now. So this is not the basis of the machine learning or symbolic AI. This is the basis of deep learning, the most sophisticated learning, the most sophisticated AI tool that we have right now. And so just to give an idea, the brain has around 86 billion neurons and around 1 trillion connections between the neurons. And interesting thing is, with all those units and all those connections, it only takes around 20 watts. The power consumption of brain is around 20 watts. So if you have to build that system in a silicon today, so I think that will be few megawatts of electric power at least to put these 86 billion units and 100 trillion connections. So until now, I talked about association and the connectionist architecture. So everything, there is a single unit called neuron, and they are connected together to learn function. So this is the fundamental. So this is a very popular picture of neuron that you see everywhere. It has one big cell body and lots of incoming connection at one end and all outgoing connection at another end. So they have name for everything. like synapses, dendrites. So let's not go into that details, but this is the neuron that you see. And this is the biological neuron. So on the computation side, we just try to model this biological neuron. So this model was first convincing model was proposed in 1943 by two scientists, McCullough and Pitt. Uh, so those so these scientists proposed some very complicated model, but they did not propose how to learn using those models. So that model didn't catch up or could not be used for actual computation too much. And there was another scientist called Frank Rosenblatt. In 1958, he proposed the perceptron model, a very simple model. And that perceptron model was shown to solve everything, like it was solution to everything in the universe. So if you look up the solution to all the questions in the universe, so it is number 42. So this is from a book. Okay, this is, I think, Hitchhiker's Guide to Galaxy. So there you will find this number 42. That is a comedy book that has no actual significance, but 42 is answer to everything. So, and this Rosenblatt designed a perceptron, and that could solve everything. So this was funded by Navy, US Navy, and it was advertised as a embryo of electronics that will be able to learn, walk, see, reproduce, and be self-aware of its existence. So it was like the hype that we have right now with large language models. So there was this hype in 1958 when US Navy funded this. So you could design everything by this perceptron. So that was not actually true. So this was the basic. This is the basics for everything that we have right now. But this was rather simple. We will see. So this. So some mathematics, some complications here. So what this perceptron model did was it took a bunch of inputs that we saw, like all these stimulus x1 to xn. It has that, and it had like connections from those inputs to some unit. So this unit like multiplied the input with these connections, like weighted this input, like x1 was weighted by w1, x2 by w2, and produce some output based on this combination of all the weights. So those combination was rather simple. It was just summation in the Rosenblatt perceptron model. So it is still the same model of neuron that we have. And when this all the combined input and weights was greater than some value, here it is theta. So the output was 1, otherwise the output was 0. So that was the first model. So why 1 and 0? Because the aim, the funding he received, Rosenblatt received from the US Navy, was to mimic the digital circuits, to produce digital circuits that can solve anything, like that can mimic any digital circuit. So just 1 and 0. So this is the model that we have and that we will work with in this presentation. So this equation, just basic algebra, can also be written. You bring the theta to the left-hand side and plus changes into minus. So, but this is the main equation. And what Rosenblatt also did was, he didn't just propose the model like McCullough and Pitt. What he did was he produced a method on how those weights will be learned. How the learning is done is you just update the weights whenever the perceptron output is wrong. So you know what is right, and you observe the output of the perceptron. You compare those two. So that will give you the error. So this t minus 0 in this equation, here. That is the error, what is the target value and what is the output. And you scale that with some learning rate, like how fast you want to change the weights, and you apply that change to the initial weights. So in this example, you change W1, W2, Wn, everything, and that way we saw that in connectionist model, when weights change, the function change, what is defined in the function change. So that is the basics of learning, or the perceptron learning rule. So another way to visualize this is every neuron here, every perceptron or neuron is just creating a plane with two regions. So one on each side. And so if we take just two variables, it can be represented by one simple line. If we take three, it will be a 3D graph. And if we take more and more, it will just be a very complicated imaginary graph that you imagine in n dimension. And this line is also sometimes referred to as decision boundary. So this defines whether the neuron output is 1 or 0. So this all comes from that perceptron model. So that is the basics. And the next thing is next important thing, and why are we working with neurons that was proposed in 1958, not with something new? And why am I presenting this is because of this theorem, universal approximation theorem. What this theorem says is any function can be approximated by using multiple layers of neurons. So the first step we saw, we can model any system by using functions. And next step we saw, and we are seeing using this theorem, that anything can be modeled by this multiple layer of neuron. Any functions can be modeled by this multiple layer of neurons. So the answer, like if you combine those two hypotheses, then you will get something that can model intelligence or any other functions using neural networks or like multiple layer of neurons. So, but highlight the term approximated. So it will not be, the theorem does not say it will exactly give the output. So it will always be approximation of the output. So this is the basis for all the research in neural network and all the large language models. And there is this is just the first step of modeling intelligence, but how to actually learn from data. So I will cover in future topics. So, but before that, let's make a very simple neuron. So I hope everyone is with me, everyone is following until now. So let's make a neuron to do AND operation. So this is the basics of AND gate. I think anyone from electronics background or computer engineering background knows it well. I think they teach this AND gate everywhere these days. So this basically AND gate, when both inputs are 1, then the output is 1. So this is the AND gate. So the primary task for today is to model this AND gate using a perceptron or using one neuron. So what you have is this equation. This will be 1 when the summation is greater than threshold. It will be 0 when summation is less than threshold. So simplifying that equation for two variables, we have x1 w1 plus x2 w2 minus theta, and x1 w1 plus x2 w2 minus theta is greater than equal to 0 and less than 0. So this is what we call in mathematics underdetermined problem. So you don't have a distinct solution for this. So there are multiple right solutions. So because there are 4 variables and 2 equations, you will never have a distinct I think there are 10 variables and 2 equations. You will not have a distinct solution. There will be multiple solutions. But let's solve this. So this will give one value. Okay, so this x1 w1 x2 w2 minus theta, this will give one value, this one very crooked circle, this is the output. So, and to convert it to 0 or 1, we will use one function known as step function. So just think step function as something that will give 0 if the input is 0. So if this input here, so if this input is less than 0, then it will be 0. So if this is greater than equal to 0, then it will be 1. So you just have to worry about the output of this and find the values of x1, find the values of w1, w2, and theta for the values of x1 and x2. That will satisfy everything. So paste, solve it, and maybe paste this in chat. Like I'll give one example. Let's say W1 is 5, W2 is 5. So plug this in with 0, 0, 5, 0, 0, and 5, 0, 0, and theta, let's say, is 10. So 0 minus 10 is minus 10. So this is greater than 0. No, this is less than 0. So this, when it is less than 0, you supply it to this unity step function. Unity step function, when it is less than 0, then this is 0. So when I put 5, 5, and 10, so this will hold true. The output will be 0. Like if I put 5, 5, 10, so output will be 0 in this case. Now test with 1. When you put 1 here, 1 into 5 will be 5, and 1 into 5 will be 5, and 10 minus 10 will be 0. So greater than equal to 0. So this will be equal to 1. When it is greater than equal to 0, it will be equal to 1. So this is satisfied. I solved the problem. But let's find another value that solves this. So I have a small program. Maybe 5, 5, 10 is not the right solution, but let me check. Where is my notebook? Okay. So I have a small program to check. I was expecting lots of answers and wrote a program to check it, but anyways. So this is unity step, perceptron, everything, and this is AND gate, 0, 1, 0 output, and I have to supply weight. So let's check if I gave you the right solution at first. I think not, because yeah, no, it didn't pass. So that was not the right solution. So it should be something, the second solution I have, or the solution that I memorized is the right solution. Okay, so this passed. So this is the solution. So what does this mean? So let's go to that. What does this mean? So we have one variable here, x1. We have another variable here, x2. So in AND gate, I gave 4 points, 0, 0, 0. This is 1, 0. This is 0, 1 coordinate system, and 1, 1. So those are the 4 points that we had. Okay, so and we got solution 1, 1, minus 1. So what we need to find is this equation. should give 1 when those variables have those value 1, 1, minus 1. So meaning it should be 1 when this 1, 1 happens, right? So in all other cases, it should be 0. So let's draw a line like this. So in this case, if you make a region like this, so what that neural network or what that equation, what those 3 variables are giving you is this line here for AND gate. So this part will always be 1, and this part, the 1 on the opposite side, will always be 0. So this is what we are learning for AND gates. So you can also change that, and this direction of this arrow will change. Like you might have some another function. Okay, so you will have some other functions, and that function might be something like this. So you can have the neuron with another set of weights, and that will learn, that will give the output pointing to this direction. So this is another neuron and another function that you are learning just by using that neuron. So, and another interesting thing that comes up, if you have to model like some certain regions, if you want output just in this region, so it will not be possible using one neuron, because one neuron can only point to one point in one direction. So what we need is, we need like at least 2 neurons. Okay, so that 2 neurons will, one will point, give one region, another will give another region, and a third neuron that will combine the output of these 2 regions. So it will be something like one neuron, and finally the third neuron. So this will take this 2 inputs. This will also take these 2 inputs. So these are these 2 lines. And to make a region, you'll need to combine those regions and produce a third. So here you need 2 layers. These are called layers. Like, so if you have this, then you can model this. Now let's model something else using neurons. Now let's model this. This looks fun. I want something that here, all this, to get the output of this region too. Let's say I'm detecting this shape. So one neuron will model this line here. So in this direction, okay, and another will model this in this inside direction. Another will model this in this inside direction, and another will model this in this inside direction. I think you are following. If you look right now, so this will all be garbage lines. These are 4, and but you like this, you also need one final neuron to combine this. So the correct answer will be 5, 4, and 5. So, and let's do one more. I will use my skill to draw something. Okay. Okay, so this is very complicated face. Okay. So this is a straight line. This is also a straight line. So this will be many. So let's see how many. 1, 2, just count the side. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so I counted 16 sides. So 16 plus 1, that will be 17. So that way you can like model like any shapes. So this is how Let's say if you had like digits, I think people know about this digit recognition or handwriting digit recognition. So to actually recognize the digits, how many you require, so that is also you can count it using these sides. So another interesting thing that neural network can do right now, from that comes from the theory of approximation, is now you can make arbitrary number of sides for any functions that you have. Like I will have one very fancy function that does something like this. So how can you model this? So to model this using neurons, what you do is you divide this, because right now in this first session, we only know about perceptron. So we only know about neurons that gives discrete values or that don't have curves, okay? So you make it divide into segments that don't have curves, and you do what is called approximation. So you have all the segments and this kind of thing. Okay, so you can follow this all the way along. So and how many neurons will this require? The one neuron will model this one, right? Another this one, this part, another this part, another this part, so on. But if you have enough neurons, then you can represent anything. These neurons and want maybe to combine these all. So with two layers, you can model any functions. So this is what is the basis of all the large language models, all the neural network research, and all the power that comes from the neural network. So I'm showing this in 2 dimensions. So how to, there is a joke how to take this to like 6 dimension. Just close your eyes, imagine for n dimensions, and then substitute n by 5. So that is how you do it for 5 dimension if you want to draw. So it's difficult to show in multiple dimensions. That is why using 2 dimensions. So, but the concept is same. So in 1 dimension, you get a line. In 2 dimension, you get a plane. In 3 dimension, you get the representation of plane in 3 dimension. What does it become? Yeah, I don't know. The concept works the same way. This is the universal approximation theorem and how you design functions. So you can make a predictor, you can make a, so this is a predictor, right? So this, how this is a predictor, you model this using neurons, and for a new input, and using, if you pass that input here, then this will be able to give you the predicted output using this neural network. So this is the prediction part. So this, that what we saw right here, this is all classification that we see, because one part is one, another part is another. So this is just binary classifier, 2, 1 or 2. So this is all using perceptrons. So that is all for this session.